Section 4.1, Laplace transforms. All right, so a little quick walk down memory lane here. What did we do in Chapter 1? More specific than just differential equations. What kind of differential equations did we solve? First order differential equations. What did we do in Chapter 2? We solved second order and higher differential equations. Right? We could solve y triple prime equations if they factored, or y to the fourth equations if they factored. Laplace transforms. What are we going to do in Chapter 4? Laplace transforms are another technique for solving first order and higher differential equations. It can be used for all. Now, primarily, we're going to use it for second order and higher. I don't think we will very often use it for first order. First order ones, with the techniques that we have, we can already solve an awful lot of first order equations. So I guess my question is, if we already know how to solve first order equations and we already know how to solve second order equations, why do we need a different way? I think when we get to it, you will definitely agree that Laplace transforms is not faster. Sometimes you can't factor, but if you can't factor, you can still usually find the complex solutions using the quadratic formula, and then we could still get our answer. All right, so here's what we learned in Chapter 2. In Chapter 2, we learned how to solve something like y double prime minus 3y prime plus 2y equals 0. That was a problem that we could solve in Chapter 2. What if I was in a mean mood and I changed the equation ever so slightly and I put in y double prime minus 3xy prime plus 2y equals 0. You cannot solve that equation with the things that we learned in Chapter 2. Because in Chapter 2, we had to have constant coefficients. So there's one of the goals with Laplace transforms, is we will be able to solve equations which do not have constant coefficients. The other thing we did in Chapter 2, we might have had something like y double prime minus 3y prime plus 2y equals some force function f of t. In Chapter 2, our requirement was that this force function over here had to be a continuous function. In Chapter 4, we will look at the same types of equations, y double prime minus 3y prime plus 2y equals f of t, but f of t does not have to be continuous. Why would we care about that? Because I said so. That's a good enough answer in itself, but there's better answers than that even.
For a certain portion, it might be continuous.
For a certain portion, it might be continuous, but then why might it not be continuous after a while? True. What I'm thinking of is, again, think of this as being a force function. Think of this as the sort of equation that came from an electric circuit.
Turn it on.
This force function might be turn the switch on, turn the switch off, turn the switch on, turn the switch off. Is that continuous? No, it's not a continuous function. Does that happen?
Yes.
Absolutely, that happens. So that would be an example of a non-continuous function that you want over here, and you want to know what's going on in your electric circuit when that happens. So that's the sort of thing we'll solve in Chapter 4. So those are the goals of Chapter 4. When you first look at it, It seems like we're doing the same thing over again that we did in chapter 2, but we're not. We're going to expand a little bit. We'll have non-constant coefficients, and we will have non-continuous functions over there. All right, so definition. The Laplace transform of f of t is, we start with little f of t. When we do the Laplace transform, we call it capital F at s. It is the integral from 0 to infinity of e to the minus st f of t dt.
Is that x multiplied by f of t?
That is multiplied right there, that's correct. For all values s for which this integral converges. What do I mean by that?
For all values.
It's going to come to a function, actually, a finite answer. But when you have an integral with an infinite bound, back in Calc 2, you learned that sometimes those converge and sometimes they don't. So if this doesn't converge, then we don't have a Laplace transform. All right, so example. Let's start with a nice simple function. Anybody got a nice simple function they like? F of t is? Well, first off, it's got to have a t in it, not an x, because I wrote f of t. 1. I wanted a simple function. There's a nice simple function. F of t is 1. If f of t is the number 1, then capital F of s is the integral from 0 to infinity of e to the minus st times 1 dt. E to the negative st. Well, t is t. T is the variable we started with. So we started with f of t. So t is the variable we started with. S, when we get all done, our new function f is going to be a function in the variable with the letter s. And so we'll just see what we get here in a minute when we integrate this. What's the integral of e to the negative st dt? I'm hearing negative s e to the negative st. That would be the derivative. I want the integral. It's negative 1 over s e to the negative st. And then we need to evaluate from 0 to infinity. So we're going to have, I should do this correctly using proper notation, this is going to be the limit as b goes to infinity of negative 1 over s e to the negative st from 0 to b. Is it 0? No, it's not 0. This is going to be the limit as b goes to infinity of negative 1 over s e to the negative s times b minus negative 1 over s e to the 0. As b goes to infinity, what happens to negative 1 over s e to the negative s times b? It goes to 0. Why does it go to 0? You're ending up with e to a really, really, really big negative exponent. E to a really, really big negative exponent gets really, really close to 0. So final answer is 1 over s.
So the dude that came up with this would be a French name?
I assume Laplace is a French name, yes. All right, so the fancy symbol we would write now, we would say, we write this is the symbol we use for Laplace transform. The Laplace transform of 1, we did all that work, we determined the Laplace transform of 1 was the function 1 over s. All right, Let's try a more difficult function. 0 would be easy. 0 would have been the easiest one. If I plug a 0 in right there, what's the Laplace transform of 0? 0, because I'm going to have 0 times anything is 0. The integral of 0 is 0. So the Laplace transform of 0 is 0. How about
3t squared.
Whoa.
let's build up slowly here. You guys are a little bit crazy. How about just t? I agree. How about just t? I don't need 3t squared yet. Although we'll do 3t squared in a minute. That should be a fun. All right. So the Laplace transform of t, according to the definition, that would be the integral from 0 to infinity of e to the minus st times t dt. How do you integrate that?
Yeah.
That's an integration by parts problem. That is correct. You didn't want it to be true, but it is. All right, so there's the first lesson of Laplace transforms. You're going to have lots and lots and lots of integration by parts. All right, so
Can we use the tabular method for this one?
you can use the tabular method for this one, but I'm not going to because I only got to integrate it once. In a minute, when I do the Laplace transform of t squared and then t cubed and then t to the fourth, you're darn right I'm going to use the tabular method. All right, so u equals t. dv is e to the negative st dt, which means du is, what's the derivative of t? 1 dt. And v is, we integrate, what's the integral of e to the negative st? Negative 1 over s e to the negative st. So I'm going to have u times v, that's t, times negative 1 over s e to the minus st, minus the integral of v, which was negative 1 over s e to the negative st, times du, which is dt. And then, after I get all done figuring this integral out, I've still got to evaluate from 0 to infinity. All right, so I'll finish my integration first. This is negative t over s, e to the negative ts. And then I've got a minus and a minus, so that's going to be a plus 1 over s. That's just a number. I can pull that out front. What's the integral of e to the negative st? Negative 1 over s e to the negative st, 0 to infinity. All right, well, I'm going to be a little bit lazy and use bad notation. I'm not going to write the limit symbol. The limit is b goes to infinity, all that stuff. You're just going to tell me what happens. What happens when t gets really, really big? What happens to t over s e to the negative t over s? When t gets really, really, really big? Gets close to 0. How come? So this one's going to infinity and this one's going to 0, but this one goes to 0 a lot faster than that one goes to infinity. If you don't believe me, use L'Hopital's rule and convince yourself. That would drop to the bottom. You take the derivative, top and bottom, and it would, so this one is 0. Plus, what happens when t goes to infinity of this one? 0. Minus. Now I plug 0 in. What happens when I plug 0 into this one? 0, because I'm plugging 0 in for the t. So that one is 0. And then I've got a minus 1 over s squared. What happens when I plug 0 in for that e? That becomes 1. So that's 1 over s squared. It's plus because I've got a minus here and I've got another minus there. So the Laplace transform of t is 1 over s squared.
There's a trend is if you did t squared, it would be 1 over s cubed.
Oh, so we have a guess. Oh, I like that when people look for patterns. So the guess is
I don't.
the Laplace transform of t squared
One.
is 1 over s cubed. That's our guess. Let's see if we're good guessers. The Laplace transform of t squared would be the integral from 0 to infinity of e to the negative st times t squared dt. And this is the problem where you have to integrate by parts, but because you have this t squared, you'd actually have to integrate by parts twice. So I absolutely agree with I would use the tabular method at this point. So tabular method, I write down my u, I write down my dv. What's u? T squared. So I take the derivative, 2t, I take the derivative again, 2, take the derivative again, 0, so that's when I know to stop. dv is going to be e to the negative st. I integrate once, I get a negative 1 over s, e to the negative st. I integrate again, 1 over s squared, e to the negative st. Integrate again, negative 1 over s cubed, e to the negative st. So I'm seeing the s cubed and the s cubed. Things are looking good. All right, so we have, remember how this tabular method works? You got a plus and a minus and a plus, and you multiply that way. So I'm going to have negative 1 over s, t squared, e to the negative st. And then the next one gets a minus, and you multiply like so. So that's negative 2t over s squared, e to the negative st. And then finally the last one gets a plus, but there's another minus here, so it's going to be minus 2 over s cubed, e to the negative st. And then we have to evaluate. All right, so once again, what happens when t goes to infinity? What happens to this first one? Again, it's in the form infinity times 0, but you drop that e down to the bottom. You can use L'Hopital's rule twice. You can show that this one is 0. And then this one is 0 for the same reason. You only got to use L'Hopital's rule once, though. And then this one is 0. So when t goes to infinity, this whole thing is 0. Minus. When I plug in 0, what happens here? 0, because t squared is 0. When I plug in 0 here, 0. When I plug in 0 there, negative 2 over s cubed. So your guess was close.
So it's n over s to n plus 1, where n is the exponent of t.
So you have a new guess. All right, so our guess was wrong, but it was close. We really needed a 2 there.
So what can we do to like guess more accurately in the future? Keep doing it and find a trend.
Keep doing it and find a trend.
So let's go up to 10.
All right, so let me ask you a question. Where did this 2 come from? It came from the t squared. We took the derivative once, we got a 2t. We took the derivative again, we got a 2, right? If I were to do the exact same thing, but start with a t cubed, I'm going to take the derivative, I'm going to get a 3t squared, derivative again is 6t, derivative again is 6. So I'm not going to end up with a 3, rather I'm going to end up with a 6, which happens to be 3 factorial. So the correct answer is the Laplace transform of t to the n, where n is a nice number, n is 1, 2, 3, 4, 5, so on and so forth, is n factorial divided by s to the n plus 1. Notice our powers go up. When we started with a t squared here, we ended up with an s cubed on bottom. When we started with a t up here, we ended up with a s squared on bottom. Max?
So are there like a bunch of different types of these? If we hit like sine t or something.
Oh, sine t. Yeah, that would be a good one.
Do they have tables like they have integration tables? Yeah, for the plots.
Sure.
Oh, really? Okay, so this is easy. Which types of
Sure, there are tables. So all we've discovered so far is how to find Laplace transforms of
t and t squared?
power functions, t and t squared. What if the teacher was in a fun mood?
You said that's only for positive integers?
That's only for positive integers. That is correct. Because if, for example, if this is a 1/2, what's 1/2 factorial? I don't know. Well, that formula only works for positive integers.
Can you use the ratio test?
What's that?
The ratio test?
The ratio test. The ratio test is for infinite series. We don't have any infinite series. Not yet. We will later in the semester.
Oh, boy.
Oh, boy.
Oh, it's fine.
All right, so my last question, what if I asked you to find the Laplace transform of 5t squared plus 6t plus 8? You wouldn't be happy? Oh, you would be happy because it's an easy question. So you're telling me I can do this? I can find the Laplace transform of 5t squared, and then I can find the Laplace transform of 6t, and then I can find the Laplace transform of 8. Why can I do them all separately like that? Because I'm going to end up integrating, aren't I? Look at your definition of Laplace transform. The Laplace transform is defined as an integral. If I'm integrating something plus something plus something plus something, I can split it up into separate integrals, can't I? That's one of the properties of integrals. And then another property of integrals is, what can I do with these numbers 5 and 6 and 8? I can pull them out front. So this is 5 times the Laplace transform of t squared,
Which we already know.
which we already know, 6 times the Laplace transform of t, plus 8 times the Laplace transform of 1. So the answer is 5 times. What did we say the Laplace transform of t squared was?
2 over.
2 over s cubed. Plus 6 times, what was the Laplace transform of t? 1 over s squared. Plus 8 times 1 over s. There's your answer.
You get one of them right?
So basically what we have learned so far today, we can find the Laplace transform of polynomials.
Why would we need to find
ln of x squared.
Why would you need to find the Laplace transform?
Yeah.
Again, eventually we're going to use this to solve differential equations which do not have constant coefficients.
Oh, okay.
So that's what we're building up to. So we can't do that right away. We've got to learn some stuff first. So on Monday we'll talk about, what if you have an e function here? What if you have a sine or a cosine? How do you find Laplace transforms of those things?